going to continue on with the concept of hypothesis tests. And this is basically what the rest of the class is going to look like. We're going to just learn all sorts of hypothesis tests or statistical inference methods, and we're going to start off with the t-test. But as the weeks go on, we're going to learn other methods. Okay, and so the t-test is used when we want to see if a numeric variable has any kind of relationship to a categorical variable. All right. So we've got so our responses. Recorded are numeric. And basically we want to see if there's a relationship between the responses and the categorical variable. Specifically for the t-test, we've got group 1 and group 2, which represent the two categories, and then they both have numeric responses. Compare the responses. So do you guys remember what I talked about when we talked about hypothesis testing last week? How do we go about a hypothesis test? First thing is we have to create a hypothesis, okay. And that first hypothesis we create is a null hypothesis. Okay. So we've got a pair of hypotheses. We've got the null hypothesis. And then we have an alternative hypothesis. Okay. 0 versus A. The null hypothesis usually says this is the truth, this is the statement, or our world is like this. And when we gather data, if our data does not match up with our statement, it's just a result of random chance. Okay? That's basically what we're saying with the null hypothesis. This is how it is, and when we gather data, if there's any discrepancy between our data and what the null hypothesis says our data should look like, it's just a result of random chance, or the random selection process. Okay? And the alternative hypothesis says, you know what? The null hypothesis is not correct. Okay? The reason why your data does not match the null hypothesis is because of random chance and the fact that the null hypothesis is wrong. Okay. So for the t-test, our null hypothesis is that the mean of group 1 and the mean of group 2 is that there's no difference between the two means. Okay? Notice I'm using mu and not y bar or x bar, okay? Because mu refers back to the population mean. Okay? So this says the mean. Okay, so basically it's saying group 1 represents population 1, group 2 represents population 2, and the means of those two populations are the same, or that there's no difference between the means of those populations. Okay? alternative hypothesis is that there is a difference, and maybe, and we have a choice of whether to say that the difference is greater than 0 or the difference is less than 0. We'll just start off by saying that there is a difference. Okay? And so here it would be interesting to us if group 1 was larger. It would also be interesting to us if group 1 was smaller than group 2. So how do we go about testing this? Okay. Well, what we have to do is we're going to look at the data that we've gathered, and we are going to try to decide if this data is possible under the null hypothesis, or if it's unlikely. Okay. And so in our book, the example is that they've selected 2 groups of rats. Okay. And they've exposed these rats to a chemical toluene. And after exposing, well, in group 1, these ones that were exposed to toluene, and then group 2 was control, so no exposure. And then the scientists cut open the rats and measured the norepinephrine concentration in the brain. Okay, so they exposed the rats and then said, sorry, we're going to cut you open and record the norepinephrine or any concentration in the brain. Okay, and these were the measurements that they recorded. Okay, so this is nanograms per gram. I don't know. However these numbers are measured. Okay, so they measured these, and these are the numbers they got. This is in your book. You don't have to copy these numbers. You can if you wish. Okay, so they had six rats in the toluene group. They had 5 rats in the control group. So these are the numbers they measured. Okay, so from this, can we say anything about the populations that they represent? Okay, so what they're saying, what they're hoping for is that group 1 represents the population. What would the population for group 1 be? Group 1 the sample that we have are 6 rats that were exposed to toluene. Okay, what population could these rats represent? Yeah, all rats possible ever that are exposed to toluene. Okay, so all rats that could ever possibly be exposed to toluene. And group 2 would be control, which would be they would represent the population of all possible rats that are not exposed to toluene. I mean, it's a little bit abstract because we're thinking there's many, many, many rats out there, and that's the truth. And so, we're not going to study the populations directly, but just samples. Okay, so our sample of 6 somehow is going to represent all rats ever exposed to toluene, and our sample of 5 are also supposed to represent all rats ever not exposed to toluene. All right, well, let's just take a look here, okay? And so we have numbers like 543, 523, 431, 635, so on and so forth. Over here we've got 535, 385, 502. So there's some overlap, okay? But it also, over here we got numbers like 385, and the biggest number we see is like 535. Whereas over here, the biggest number we see is 635, and then we get numbers like 431. So it seems like this at least has a higher upper range, and this has a lower, the bottom, the minimum is smaller over here, but does that mean that the means are truly different, or could the means still be the same, and we just happen to get different rats, and this one, so there's a bunch of questions we're not entirely sure about. Because somebody could just say, oh, you know what, toluene makes no difference on norepinephrine concentration, and if you were to just pick 11 rats and put 6 in one group and 5 in another group, you could very well end up with these numbers and these numbers, just because of the random assignment of rats and things like that, right? Somebody could say that. And you'd say, oh, well, maybe that's true. Okay. Well, let's take a look at the means of each of these groups. Okay. So if I calculate the sample mean, so the sample mean of group 1, which will be y bar 1, I just add up the 6 numbers and I divide by 6. I get 540.8. Agree. And then if I do y bar of group 2, I get 444.2. Okay. So the observed difference, this is the observed difference between means. This is equal to some number, a little bit less than 100. Okay, it's like 96 or something, 96.6. Okay, yeah, 96.6. If the null hypothesis were true, okay, meaning the mean of group 1, or the mean of the population 1 and the mean of population 2 is truly 0, okay? So if the null hypothesis is true, that means toluene has no effect on norepinephrine concentration. The mean of population 1 and the mean of population 2 are the same. There's no difference between them. We would expect, what would we expect this number to be? Anytime I take a random sample of group 1 and a random sample of group 2, we would expect the difference between them to be, yeah, we would expect it to be 0, okay? So if the null hypothesis were true, we expect y1 bar minus y2 bar to be 0. Okay? Or at least close to 0. Okay? And here we're observing a difference of 96.6. So the question is this difference of 96.6? It's not 0, but is it a big deal, or is it not a big deal?
When it says or close to 0,
Yeah.
That's just like an arbitrary decision that you have to make? Like if the number is close to 0?
Oh, okay, so we'll use statistics and our knowledge of probability to answer what is close to 0 and what's not. Okay, but this is just the general concept, okay? If the average of one thing and if the average of group 1 and the average of group 2 are exactly the same, anytime I take a random sample from group 1 and a random sample from group 2, I would expect the means of those samples to be about the same, or that the difference between the means would be close to 0, right? That's what I'm expecting. But what we're seeing is a difference of 96.6. And so we have to somehow make a judgment call on whether this difference of 96.6 is it a big difference or is it not a big difference? Okay, yeah, Lisa.
Wouldn't it be a big difference based on your numbers? Like, since your number is like 500, I mean, it's like, you know, you're like mean average, you know, based on those like 540, so you're saying that it's like probably about a fifth of
Okay.
your mean, so it would be a large difference.
Okay, yeah, you know, so that's a good point. That's not how we're going to evaluate it, okay? Because what we're not going for, okay? The key isn't whether 96.6 is a large proportion of these numbers, okay? The key is how does 96.6 compare to the spread or the standard deviations of these numbers, okay? That's what we're going to compare against. So these numbers exhibit some kind of variation, and these numbers exhibit variation also, okay? And so the question is this difference of 96.6, is it large or not compared to the variation exhibited by these numbers? So we saw a measurement to kind of to measure the variation that exists in these numbers. Okay, what is that? Okay. We've got the standard deviation. Okay, but in particular, when we're talking about samples, what are we dealing with? Well, ideally, we could deal with the standard deviation of the sampling distribution. Okay? That would be the sigma over the square root of n quantity. All right? But again, we don't know sigma because sigma is the population standard deviation. So we have to use what instead? The sample standard deviation, S. Okay. So we're going to use S instead, and we call that the standard error when we use S. Okay. So to decide whether or not this difference of 96.6 is large or not, okay? And here, the standard error is going to be the standard error for a difference of two sample means. Okay, so this is the standard error of y1 bar minus y2 bar. And I don't know if you guys remember this, but this is S1 squared over N1 plus S2 squared over N2. This is the standard error of a difference between means. That is kind of familiar, right? We saw this when we did confidence intervals. Okay, so I just want to make sure everyone's okay so far. So what we're saying is that if the null hypothesis were true, we're expecting a difference of 0 between sample means. What we happen to observe is not a difference of 0. We observed a difference of 96.6. And now we have to make a judgment call. Is this 96.6 large or not? Is it a big deal? Should we worry about this difference? Or is it within the realm of whatever we would see just by random selection anyway? Okay. So to decide whether it's big or not, we're going to compare this to our standard error. So the standard error requires us to figure out the standard deviation of each group. So you guys know how to find standard deviations of numbers, but rather tedious. So I'm just going to have the computer or the book tell us, or we could ask a calculator or whatever. And get this, all right? And so my standard error here, standard error of y1 bar minus y2 bar would be square root of 60 96.1 squared over n1, which is 6, and 69.6 squared over n2, which is 5. And when you do this, you get 41.195. Alright, so this says the standard error, which is kind of an estimate of the standard deviation of the sampling distribution, okay? It says the standard error is 41.195, and I'm observing a difference of 96.6. So this puts me at about a little over 2 standard errors away from what I'm expecting, okay? So at this point now it's almost like I'm finding a z-score, right? So how many standard errors am I away from what I expect? Okay, so this is what we call the test statistic. So it's not a z-score. Maybe it could be a t-score, but we call this the test statistic. Okay. And all test statistics, when we go into future hypothesis tests and things that aren't t-tests, okay, they're almost all going to follow nearly this idea here, okay? We've got whatever we observed, and we say how far is it from what we expect, and we divide by the standard error. Okay? So it's almost a similar form as the z-score, right? The z-score is the mean is here, and what we observed is over here, and we're dividing by the standard deviation to see how many standard deviations we are from the mean. No longer are we dealing with the mean, we're dealing with what we expect. So what we observed is a difference of 96.6. We're expecting a difference of 0. And our standard error is 41.195. So that tells me my difference of 96.6 is 2.34 standard errors, okay, away from what I expected, which was a difference of 0. Okay. So is 2.34 a big deal or not? It kind of is, right? It feels that way at least, all right? Well, at least when we deal with, if we were dealing with the normal distribution, we know that anything more than 2 standard deviations away puts us, you know, in the upper, lower 2.5%, right? And now we're 2.34, not standard deviations, but standard errors away, okay? So again, because we're not using standard deviations, and we don't know the true population standard deviation, we've got it, and we're like fudging the numbers a little bit by using our sample standard deviation as a guess. We have to use the t distribution rather than the normal distribution, okay? So that's why it's called the t-test. All right, so we have to decide, we have to look up 2.34 in our t distribution to decide whether or not this is a large difference or not, okay? Or to see the probability of getting 2.34. Okay? So we look up 2.34. And again, it's the t distribution because we are using standard error rather than the known standard deviations, okay, which are unknown to us. So we don't know. And so the compensation thing is. Okay, so how does this work? Okay, we got to figure out our degrees of freedom, all right? And again, degrees of freedom is the true formula for finding degrees of freedom is difficult for us to use. So we're just going to approximate it using n1 plus n2 minus 2, okay, which is going to give us 9. So this is approximately 9 degrees of freedom. A computer will give you a more accurate number, but this is good enough for us. Okay. Alright, so this is, we're going to use the t-test, or t-table a little bit differently. We're going to the row 9 degrees of freedom, and I'm just going to copy the numbers that I see there. I got 0.883, 1.383, 1.833, 1.973, 2.15. Oh man, I'm gonna run out of space. 2.26, 2.398. I'm just gonna have to stop there. Okay, and then the upper tails go 0.20, 0.10, 0.05, 04, 03, 025. Okay. Did I copy those numbers right? 3, 9, 8. Okay. So our test statistic is 2.34. Okay. So the way this works, and this says upper tail probability. So let me just take a break and explain how this table works. All right. So, is it alright if I erase all this over here? Okay. Alright, so the t-distribution looks a lot like the normal distribution. Centered at 0. And basically what this says, it says if you have a t-distribution with 9 degrees of freedom, and you were to draw a vertical cutoff line at 0.883. Okay, so if I go out to 0.883, I draw a line right here, the amount that's in this part, what's known as the upper tail, the amount up here is 20%. That's what this table says. Okay? So then it makes sense that if I go further away to 1.383, so no longer at 0.883, but I draw a line now at 1.383, the amount that's over here in this tail is 10%. Okay, so I've got 10% between here and here, and I've got 10% beyond there. All right. Okay, so what this says is that my test statistic is at 2.34. Okay, so what I want to know is how much is in this tail at 2.34. Okay. Well, we don't see 2.34 in the table. Okay. But what we do see is we see 2.398. So it says if I draw a line here at 2.398, I have 0.02 in this tail. I got 0.02 over here. And if I draw a line at 2.26, and the amount that's over here, how much is over there? 0.025. Okay. But now I'm drawing a line at 2.34. So how much is beyond 2.34? Well, the answer is we don't know. Okay, we don't know. We can't give you an exact number, but I can tell you it's going to be more than 0.02, but less than 0.025. Okay, can we all agree on that? Okay, so the tail probability we don't know exactly what it is, but we do know for sure it's going to be less than 0.025 and more than 0.02. Okay, so 0.02 is less than the tail probability, which is also less than 0.025. And this is totally fine. Okay. So our tail probability, we don't know exactly what it is, but we do know it's between 0.02 and 0.025. Okay? And all I'm doing is basically I'm just saying, where does 2.34 fit? It fits in between here, so we know that our tail probability is going to be between here. Okay. So, what we have here, okay? So how does this relate back? What this tells us is that when we observe a difference of 96.6 with a standard error of 41.195, okay, that puts us at 2.34 standard errors away from what we're expecting. The probability of being 2.34 standard errors larger than what you expect, okay, so larger than your 0 point, the probability of being 2.34 standard errors or more away is between 2 and 2.5%. That's what we're saying. Our null hypothesis says that we expected a difference of 0. Okay. Our alternative hypothesis says maybe that difference does not equal 0. Okay. So our alternative hypothesis is equally interested if group 1 was larger than group 2, okay, which is what we have here. It would also be interested if group 1 were smaller than group 2. Okay. So we observed a difference of 96.6. It would also be interesting if, because the labels are arbitrary, if we had seen a difference of negative 96.6. Okay. So the total probability, okay, so we have to ask, okay, so the total probability of us seeing a difference of 96.6 or more, positive or negative, is not between 2 and 2.5%, but is actually between 4 and 5%. I'm doubling this because both the negative and positive differences are of interest to us. Okay, I know it might feel a little confusing at first, but we'll get used to this. Okay, so because the alternative hypothesis, I guess maybe interested is not the proper word to say, okay? It's not that this has feelings or thoughts, but is interested in both a positive or negative difference. Okay, we will double our tail probabilities. So our probability, which we call the p-value, is going to be between 4 and 5%. Yes, Tony.
Is this because it's like you did this one time and then you switched the numbers and did it again and got a negative one and then you're taking both of those?
Not exactly, okay? Well, what we're basically saying is that, well, let me just back up and explain a little bit, okay? So I think I talked about the p-value last week, right? A little bit, okay. Does anyone remember what the definition of a p-value is, or what a p-value is? What is a p-value anyway? not the probability of observing the null hypothesis. It sounds like that, but it's very different from that.
The probability of observing the data.
Yes. It's the probability of observing the data, or something more extreme, if the null hypothesis were true. Okay? So just remember this. The p-value is the probability of observing your data for something more extreme if the null hypothesis were true. Okay, that's the p-value. And so our data, okay, what we've boiled our data down to, our data were all of these 11 data points with their standard errors and things like that, okay? But what we've boiled our data down to was a difference of 96.6 and a standard error of 41.195, or a difference that was 2.34 standard errors away from what we expected, okay? So the probability of observing something that will give us 2.34, that's 2.34 standard errors away from our what we expect, the probability of observing that, or something more extreme, okay? So that's why we're doubling it, because positive 2.34, so 2.34, 2.35, 2.36, anything higher than 2.34 is more extreme, and then anything more negative than negative 2.34 is also more extreme, okay? So because of the symmetric nature of the t-distribution, we're doubling this. Yes, Tracy?
So, when you're saying that the tail probability was 2 point something standard deviations, the percentage of that being between 2 and 2.5%.
Yes.
So then what, I'm confused about what the other 98% would be. Is that what you mean by something more extreme? I'm not sure if I'm asking
So
correctly.
we boiled our data down to this test statistic of 2.34, okay? And so data that's more extreme, okay, so we are at 2.34 standard errors away from, just for lack of a better word, mean, or what we expect, okay? We're 2.34 standard errors away from our expectation, okay? So anything more extreme would be anything over here. This is more extreme than 2.34. Okay. However, our our alternative hypothesis says that the difference between the two is not equal to 0. So we are interested if mu1 was larger, or if mu2 were small, or if mu1 was larger or smaller than mu2. Okay, we're equally interested in these. Okay, so if I just said, you know what, I have no idea, okay, here's group 1 and here's group 2, I don't know if one's going to be larger or smaller. I just want to see if there's any kind of difference, okay? So in that case, going out 2.34 in this direction would be equally extreme, and anything beyond negative 2.34 is more extreme. Okay, is that right? So this is also more extreme than what we observed. So how much is in the tail over here? Do we know? How much is beyond negative 2.34? Well, the answer to how much is beyond negative 2.34 is going to be the same as how much is beyond positive 2.34, because it's symmetric. Okay? So I don't know exactly how much is beyond positive 2.34, but I do know it's beyond between 0.02 and 0.025. Okay? So basically, what I could split this down to is that this thing, whatever it is, the lower tail is less than 0.025 but bigger than 0.02, okay? And the upper tail is between 0.02 and 0.025. So how much is, if I added the two tails together, how much is in the total, two tails combined? I don't know exactly, but I do know it's going to be between 0.04 and 0.05. Because I'm adding those two together. Okay, so that's why I'm doubling it and getting this. Is that all right? Okay, so we get a p-value between 4 and 5%. And so this says the probability of observing our data, or something more extreme, if the null hypothesis were true, is between 4 and 5%. So again, if there really is no difference between rats exposed to toluene and rats exposed to nothing, okay, the control rats and the toluene rats, if there really is no difference between those two groups, what's the probability that I select 11 rats, get a difference of 96.6 and a standard error of 41.195 or something more unusual than that? What's the probability of that happening? It's between 4 and 5%. So what do we say? Does that mean, would we say we don't have any evidence that toluene makes a difference, or would we say we've got evidence that toluene makes a difference?
Do you have evidence that makes a difference?
Maybe, yeah. It depends how, I guess, how certain you want to be, right? Okay. So it depends, right? So at some point you've got to make a judgment call, and if somebody says, okay, well, does toluene make a difference on the norepinephrine concentration in a rat's brain? Okay. You say, well, okay, I did an experiment. I did it on 11 rats, and at this point, I feel like I've got some evidence that it makes a difference. Okay. So, well, that's if you consider 5%, anything less than 5% is a significant number. That's if that's what your level of significance is. Okay. So if we say p-values less than 5% are significant, and we conclude that we have evidence that this drug, chemical, has an effect. And that's what we conclude here. Okay. So that's how a basic t-test is conducted. And then so we'll talk about maybe some subtle changes that can happen depending on situations. Okay, can I erase the lower half here? different test, okay? So let's say, okay, let's say somebody wanted to know, does drinking alcohol affect your reaction times? So we would have a control group. These are people who didn't drink any alcohol, and then we would have a test group. Okay, people who drink. Give them some drinks. Okay, so we do some kind of experiments. We got group 1, and this would be control, no alcohol. Group 2. Okay, give them. These people drink alcohol, and then. All right, so you know, if this is a properly done experiment, you would make sure everybody drinks the same amount of alcohol. You should control all of these other things, right? And the only difference between group 1 and group 2 is the fact that the amount of alcohol that they drank. And then you do some kind of test, right? I don't know. A light flashes on the screen, they have to hit a button or something. Or maybe they hear a sound and they hit a button to say, okay, I heard the sound. All right, and we measure their reaction time in milliseconds. Okay, so let's say we have 380, 420, and okay. So I'm just making up terrible numbers here. I have no idea. And okay, and then over here. Okay, well actually, before we even looked at the data, do we expect alcohol to make a difference on reaction time? Yes or no? Yeah. Okay. And what do we expect the difference to be?
Slower.
Okay, we expect people who, after they've had a few drinks, to have a slower reaction time. Okay, that's what we're expecting. So, if we set up our null and our alternative hypothesis, what would our null hypothesis be?
There's no difference.
Is that there's no difference between reaction time, the mean reaction time of the control group, the control population, and the alcohol population. Okay, so if somehow we could force everybody to drink alcohol and also record their times when they were completely sober, and figure out the average reaction time, we would see no difference. That's the null hypothesis. And the alternative hypothesis, okay, group 2 is the alcohol group, and we're expecting them to be slower. mu1 minus mu2, this is, again, we're recording reaction time, would be what? A negative number, okay? Because we're expecting these numbers, these people, to take longer to respond, right? Okay. So in this case, we're only interested if we have evidence that alcohol slows down those reaction times, okay? So this is what we call a directional test. And only interested to see if the alcohol group has larger reaction times. Okay. So anyway, we record the reaction time for group 1 and then the reaction time for group 2. Okay. Let's say we looked at 6 people in group 1 and 6 people in group 2. And let's say the average reaction time here was 390. And let's say, what if the average reaction time here was 380? at this point, if somebody says, okay, you're in some research lab and they say, okay, we're giving you money and do this experiment, but we don't have that much money, so you can only do it on 12 people total. So you do this, okay, and these are the results of your experiment, right? And then so your boss comes up to you and says, okay, so you did your experiment. Do you have evidence that alcohol slows down reaction time? No. No. At this point, it seems that alcohol, if anything, speeds up people's reaction times. Okay? Alright? So if you get data like this, okay, and somebody says, do we have evidence that alcohol slows down reaction time? No. The answer is no. Okay, and that's because you just have to do, I call it the common sense check, okay, but the book calls it checking directionality. You just have to make sure that your data just makes sense to use for your alternative hypothesis, okay? So our alternative hypothesis is expecting that the alcohol reaction times will be larger than the control alcohol times. And what we're seeing is that our data does not support that at all, okay? So, no, what do I say? Okay, so, y1 bar minus y2 bar is greater than 0, okay, which does not match the alternative hypothesis. So at this point, we have no evidence to support the alternative hypothesis. Okay? No evidence to support the alternative. So we have no idea, okay? Well, alright. So if I said, well, can you give me a p-value? What would be your answer? Well, okay, so the truth is we can go through some process and find a precise p-value, okay? But if somebody just says, okay, well, would your p-value be large or small? What's your answer in this scenario? It would be large. It would be large, okay? Now it sounds weird. It sounds weird, okay? So the p-value is what's the probability of observing your data or something more extreme if the null hypothesis were true. Okay? So if our null hypothesis were true, we're expecting differences of 0. Okay? The definition of what is more extreme is defined by our alternative hypothesis. Okay? So our alternative hypothesis would be, what we observed is a difference of 10. Okay? So our alternative hypothesis is things that are more extreme are differences of 10 or anything smaller than 10 or more negative. Okay? So 10, 9, 8, 7, 6, 0, negative 1, those are all more extreme than a difference of 10, because here we're looking for the less than direction. So if the null hypothesis says that the difference, we're expecting a difference of 0, okay, our p-value, the probability of getting a difference of 10 or less is going to be over 50%. It's going to be over 50%. Okay? So anytime you get something where your data just goes in the opposite direction of what you're expecting from the alternative hypothesis, okay, you can just stop right there and say, well, I'm not going to continue on with this thing because my data is certainly not going to support the alternative hypothesis. It doesn't prove that the null hypothesis is true, but our data certainly doesn't support the alternative hypothesis, and we can just say my p-value is going to be large, bigger than 50%. Is that okay? All right. So let's rewrite some of this, okay? And let's just say, okay, well, you're like, nah, that can't be right. Okay? You tell your boss, well, I tested 12 people, and I thought they were randomly selected, but I must have gotten some randomly selected people who just had a little bit of a weird reaction time. So just give me a little bit more money. I got to do some more research, okay? You say, okay, well now, all right, fine. Now we've given you money and you can test 12 in each group or something, okay? I'm just setting the group size to be equal. It doesn't require, to do a t-test, you don't need equal group sizes. All right, so after you redo the thing, or you gather more data, okay, maybe you get a reaction time. I think I'm using the same numbers here. I don't know. Okay, 380 and 460. Okay, and then let's make a standard deviation of 60 and a standard deviation of 90. Can you complete the rest of the t-test here? Or at least, let's see if you can figure out the test statistic here. So I'll give you guys a moment to do some work and see if you can find the test statistic. And the test statistic is equal to what you observed minus what you're expecting, divided by the standard error. So try that out. we got, I got a test statistic of 2.56. Did I do my math right? Okay. You guys did it right also. Alright. Are we good? Did anyone not get this?
I have
Yes.
one question.
Yeah.
So when you subtract them and it ends up being negative, right? that was
Oh,
my
I'm sorry,
question.
I'm sorry.
Yeah.
Negative,
Okay.
sorry, thank you, thank you. Negative 2.56, yes. It does make a difference. Okay, so this is what our picture looks like. Centered at 0, negative 2.56. Alright, and because our alternative says less than 0, to be more extreme means to be more negative than negative 2.56. We're asking, when we ask what's the p-value, we say what's the probability that we would get data, or we're getting a difference more negative than 2.56 standard errors away from what we expect. Okay. So we go to our t-table. How many degrees of freedom do we have in this situation? 22, approximately 22. Okay. Now the t-table only gives us positive values, but because it's negative, you can just ignore the sign, and the amount above positive 2.56 is the amount below negative 2.56. So we look at 22 degrees of freedom, and the relevant numbers are 2.183 and 2.508. Is that right? I'm gonna get like a ruler. Yes. Okay. So 2.56. Oh no, that's actually I'm doing my math wrong. 2.819. That's the number I want. Okay. 2.508, 2.819. Okay. And 819 corresponds to 0.005, and this corresponds to 0.01. And so, again, we don't know exactly how much is beyond 2.56. 2.56 is somewhere in between 2.508 and 2.819. So we don't know exactly how much is beyond there, but we do know whatever that number is, it's going to be between 0.005 and 0.01. So the amount over here, the tail, is between 0.01 or 0.005 and 0.01. An exact number we don't know, but it's between half of 1% and 1%. That's a probability that we select 24 people, 12 in each group, where we're observing a difference of 80, where the standard error is 31.224, or something more extreme. Okay, and again, but this time, because we're only interested in a more negative difference, I'm not going to bother with the positive side. Okay, so I'm only interested in a more negative difference. I'm not going to bother with the positive 2.56. So here, my p-value is the same as our tail probability, between 0.005 and 0.01. That's my p-value. Alright, so then at this point, do we say we have evidence that alcohol impairs reaction time? Yes. Okay. Because for us to believe that alcohol does not slow down or hinder someone's reaction time, that would mean, okay, If alcohol truly had no effect on reaction time, then that means we were one of the lucky 1% or fewer than 1% of experiments that gave us a result like this. Okay? Because it's true, this result could happen by random chance, even if people who drank alcohol and people who haven't drank alcohol truly had no difference in reaction time. Our experiment could give us a difference of negative 80 points and things like that. It could happen, but the probability of that happening is less than 1%. Okay? So rather than saying, oh, we were just that really lucky or unlucky 1% of people where this thing happened, we're going to say, my initial assumption about there being no difference is probably wrong, and I've got evidence that alcohol impairs reaction time. I just want to make sure that line of thinking is working. Alright, so just to summarize, the difference between a directional and non-directional test. Okay. So just the null hypothesis will always have an equal sign. Okay. Okay. But the alternative might have different ones. Okay. So if the alternative has not equal, it is a non-directional test. Okay. Find the tail probability and then double it. If the alternative has greater than or less than, check directionality. So check to make sure that your data supports whatever the alternative hypothesis is even claiming. If the data doesn't support the alternative, then you can stop and just say no evidence. No evidence to support the alternative. On the other hand, if the data could support alright, continue on with the test, and whatever your tail probability is, that's your p-value.
So when you say non-directional, you mean it's two-tail? and
Yeah,
if
two-tail.
it's directional, it's just a single tail.
Yes. So, yeah, directional and one tail are synonymous, and non-directional and two tail are also synonymous. Okay. Non-directional, same thing as two tail, and directional, one tail. So let's talk about the conclusions we make. Alright, so you go through your test and you find a p-value. Oops. Well, you get a test statistic. You look that test statistic up in the table, and you get a p-value. I know, this class we don't talk about where those tables come from, why we would have these numbers in the tables. The tables are just kind of this thing that you use, and they give you p-values. And it's not really in the scope of the course to talk about that. If you're interested as to why the tables have these numbers, you can take a mathematical statistics class if you like calculus and stuff like that. If it's not your thing, just don't bother. But that's there. Okay. Alright, so you get a p-value, and then what we decided, and remember, the p-value is what's the probability of observing your data, or something more extreme, if the null hypothesis were true. Okay, and this is definition that's going to come up over and over and over again. Okay. P-value is the probability of observing your data or something more extreme. If H0 were true. Okay, so if the p-value is large, then we